For the first question, we're asked to estimate the pKa of the most acidic proton on the following compounds. For this, it's good to look at the pKa table. So I'm going to drag that over here. So we have an alcohol functional group on an aromatic ring. So based on the pKa table right here, an alcohol functional group on an aromatic ring, the pKa is about 10. But we have a strong electron withdrawing group on it. Unfortunately, we do have on our pKa table a strong electron withdrawing group, our NO2 group. And it looks like then the alcohol functional group, that's a much more acidic proton. The pKa has dropped all the way to 7.1. So fortunately, we were given the answer for this one. So for our pKa values, this one is 7.1. Now, on that pKa value, like we saw, if you have just an alcohol functional group on the ring, just an aromatic ring with an alcohol functional group, that pKa is about 10. From what we saw at the end of the chapter, if we have an alkyl group on the ring, that's a weak electron donating group. So I would say since we're donating more electron density into the ring, this oxygen would be slightly less stable with that negative charge. So I think it's going to increase the pKa just slightly. So I'm going to guess about 10.2 on that. Anything around that area would be fine, as long as your estimate for this pKa is less than what is your estimate for this one. So here we have an atom that can donate electrons into the ring via resonance. So we have a strong electron donating group here, so I would expect the pKa of this to be even higher. We would be less stable with the negative charge on the oxygen for this one. Again, not that high, not extreme. So if you look up the literature value for the pKa, it's around 10.4, but I'd accept anything higher than 10.2 as long as you don't go over like 12 or 13. All right, for the next one, show the mechanism and predict the products of the following reaction. Here we have a mono-substituted alkene. Here we have a di-substituted alkene. So this alkene is slightly less stable, so it's probably going to first be protonated by our strong acid, which gets us to our intermediate, which is that alkene still there. That's what has the hydrogen attached now. And now we have a positive charge on this carbon. We're definitely going to put the hydrogen there because our positive charge needs to be on the more substituted carbon. Now, if this said 0 degrees Celsius or it said do a 1,2 addition to this, then I would have my Br minus come in and attack that carbon. But it's not. We're at 40 degrees Celsius, so this needs to be a 1,4 addition. We put the hydrogen at carbon number 1, which means we need to put the bromine at carbon number 4. That's going to make more sense when we show the other resonance contributor for this. So now we have our alkene, and now we have a positive charge on our secondary carbon, and now our Br minus can come in and attack that carbocation to give us our final product, which is Br there and our alkene there. So that is our 1,4 addition product. For the next one, predict the product and draw the mechanism for the reaction. So here's our diene. We have 2 alkenes. Here's our dienophile, an alkene that's got electron density pulled from it. So if we imagine this carbonyl carbon, specifically this oxygen pulling electron density from here, we'd end up with a positive charge on that carbon. For this, it's a one-step mechanism, and it's going to be easier to redraw this since this isn't in a cis-diene conformation, and this is a little bit tilted. I think it'd just be easier to redraw it. So we will put our double bond oxygen there, that's there, and then for our diene, we've got our methyl group on that carbon, which is that carbon, and then I basically just rotated around this carbon here to put my alkene facing down here, and then I turned it a little bit to make it look like that. So now I've got it lined up and essentially close to our cyclohexane formation. Again, the carbon that is our electrophilic carbon is right there. So we're going to use one of these double bonds to attack that carbon there. We're going to use these electrons to come up and attack that carbon there, because these electrons are going to move down and stabilize the positive charge that theoretically would have been there. So that gets us to our final product, which is a 6-membered ring where we have a methyl group there, our alkene right there, and we have our carbonyl carbon attached, which is a ketone functional group there. Now, it's debatable where this methyl group would go. We haven't covered this in class in detail. So if you were to actually put the methyl group there on your product, I would give you full credit for that as well. All right, for the next one, determine the reagents, including isopropyl benzene, needed to make the following compound. So we were given one of the reagents already, so benzene with an isopropyl group on it is one of the reagents. And the other reagents, we need to get to this. So this is the carbonyl carbon that we need to add. So writing this, I would start by drawing that with the chlorine. And then we've got two CH2 groups and a CH3 attached. And then AlCl3, or aluminum trichloride, will help make this carbonyl carbon even more reactive. So looking back, I got a little bit caught up on this. I probably should put the isopropyl group on the bottom just so that it makes a little bit more sense and everything lines up for how we get to our final product. So putting the isopropyl group on the bottom, it looks like that. So now this carbon, specifically that double bond, is what is going to attack that carbon once we show it has the positive charge on it after interacting with our AlCl3. All right, for the last question, determine the reagents and propose a mechanism for converting benzene to 1-bromobenzene. So the easiest place to start is go ahead and draw benzene. We know that's a starting material. We know we have some reagents there. When we add bromine, we know we need Br2 as a starting material, and FeBr3 or AlBr3, doesn't really matter. And we are going to make 1-bromobenzene with that. All right, for the mechanism, our bromine is going to attack the iron here to make FeBr4. And I'm going to actually draw the mechanism up in this area here, just because I ran out of room on this paper. So once we have our FeBr, and then bromine attacked that. So bromine's there now with a positive charge, and we have bromine there. And our iron has a negative charge. Now the aromatic ring can attack. Our bromine. That's a great leaving group since it has that positive charge on it to get us to our intermediate. Br with a plus charge there, and that there and that there, and then we need a weak base to deprotonate that to get us to our final product, which is that compound right there.